In this video, we will complete the proof of the second isomorphism theorem for rings. And I want to start by doing a brief synopsis of the previous videos. We know that R is a ring, we know that I is an ideal, we know that S is a subring, and we've shown that I is actually an ideal in the subring S plus I, and as a consequence, we can create a quotient ring on this side of our diagonal, and the quotient ring on that side of the diagonal is S plus I mod I. We've also shown that S intersect I is an ideal inside the subring S, and so we have a quotient ring on this side of my diamond, and this quotient ring is S mod S intersect I. And the second isomorphism theorem says these two quotient rings are isomorphic. Now, in the previous videos, we have found the following facts. We have found out that S plus I mod I is nothing more than the left cosets S plus I, where the representative is pulled from the subring S. And we have also defined a map phi going from S plus I mod I to S mod S intersect I, given by the formula phi of S plus I is just going to be S plus S intersect I. And we have previously shown that phi is well defined, which is an issue because cosets always have multiple names, and we have also shown that phi is a ring homomorphism. So all that we need in order to complete the proof is we still need to show that phi is onto and one-to-one. So that's what we'll be doing in this particular video. Well, let's see. Phi is onto. To show that phi is onto, we have to start by picking an arbitrary element in the codomain of the function. In other words, we have to pick an arbitrary element like C plus S intersect I that belongs to S mod S intersect I. And we need to find somebody in S plus I mod I that is sent to this particular coset by our map phi. Now, what I want to notice is that this particular statement here implies that C has to belong to S, and this is because S mod S intersect I is the collection of left cosets that look like S plus S intersect I, where little s is pulled from set S. And it's important that C is inside S because that tells me that C plus I belongs to S plus I mod I, which I know is the set of left cosets that look like little s plus I, where little s belongs to the subring S. And since C plus I belongs to the quotient ring S plus I mod I, that says we can do the following. We can feed it to phi. But phi of C plus I is just going to be C plus S intersect I. And that's enough to say phi is onto its target ring of S mod S intersect I. So onto is done. Now what we need to do is we need to turn our attention to showing that phi is one-to-one. Now, there are several ways of doing this. What I want to do is I want to use the fact that a ring homomorphism is one-to-one if and only if its kernel is trivial. And meaning its kernel is trivial means that the kernel contains only the zero element in the domain ring. And in our case, that would be the zero element in S plus I mod I. So because kernels are the things that get sent to zero inside the target ring, and we're hoping to show that the kernel is just this one element inside the domain ring, I want to talk about the zero elements inside the two quotient rings. So the zero element inside S plus I mod I is just going to be the zero element inside S plus I, but that's going to be 0 inside R, plus the ideal I. And the reason why is that the zero element in R is inside the subring S plus I, and that's why the zero element inside this particular quotient ring is that particular coset. Well, we have a similar thing going on in our target ring. The zero element in S mod S intersect I is going to be the zero element in R plus our ideal S intersect I. And this is also because the zero inside our big ring R has to belong to S, since S is a subring. And while I'm writing reasons, I should have said that this particular statement is true because S plus I is a subring. And these are both subrings of our ring R. So we now know what the zero elements are. And at this point, we can now meaningfully look at what is the kernel of phi. So what is the kernel of phi? Well, our goal is to show that it only has that one element, which is the zero element in S plus I mod I. But I want to basically look at this by simply assuming, so we're going to let, let's call it little a plus I, be inside the kernel of phi. Now, what does that tell me? First of all, it tells me that a plus I is part of my domain, which is S plus I mod I, and that is the set of left cosets that have representatives inside the subring S. And so all of that tells me that A is indeed inside the subring S. Now, there's another thing that I also know, is that if I let phi equal a plus I, the fact that a plus I is supposed to be inside the kernel of phi, that says phi of a plus I has to be the zero element inside S mod S intersect I. And this statement is going to tell me that a plus S intersect I is going to have to be equal to 0R plus S intersect I. And I want to kind of make sure that I understand that this here is equal to that, and this is equal to that. So we can go from this step to this step because of the definition of phi and the definition of the zero element inside the target ring S mod S intersect I. But now what we've got is an equation. So this is an equation in the ring S mod S intersect I. And I know when two cosets are equal to each other. Two cosets are equal when the difference of their representatives lies inside the ideal. And so what we now have is this. A plus S intersect I equals 0 plus S intersect I is going to imply that A minus 0 has to belong to S intersect I. And of course, A minus 0 is just A, so we now have A is inside S intersect I. Now that tells me that A is inside S and A is inside I. And this second thing is very important. And I want to look at the consequence of that. Since A lives inside I, we know that A plus I is actually just 0 plus I, and this is true inside both the quotient ring R mod I and inside its subring S plus I mod I. And what this says is that we've now proven the following implication. So we have A plus I belongs to the kernel of phi implies A plus I is exactly equal to the 0 element inside our domain ring S plus I mod I. And so this says that the kernel of phi is indeed trivial. It only contains the 0 element of S plus I mod I, and that says phi is indeed 1 to 1. And what that means is that phi is now a ring isomorphism, and hence we have now finally shown the end of the proof of the second isomorphism theorem for rings. We now know that the quotient ring S plus I mod I is indeed going to be isomorphic to the quotient ring S mod S intersect I. And that completes our proof.